We're ready to go. So, this might seem kind of silly and obvious or whatever, but with in some of the properties of a square that we're going to need to know, 4 sides congruent. And all 4 angles are right angles. Now, there's some additional problems involving like the diagonals of the square and that sort of thing, but we don't need to necessarily do that with what we need to do with this. So I'm going to mixture with that. Lateral that we will be investigating is the right angle. Now in a right angle, you also have 4 right angles, but the opposite sides are the same length. So not all 4 are the same anymore. These 2 are the same, and those 2 are the same. Okay, now into some ones that maybe you don't remember quite as well. So we've got this guy. That is a trapezoid. Yep. In a trapezoid, we have 2 bases that are different lengths, and then we have 2 legs that are the same length. If it is a certain type of trapezoid, in this case it is an isosceles trapezoid. Well, the only thing that you need to be a trapezoid are 2 sides that are parallel. Okay? That's it. And a lot of people don't know that. A lot of people assume just like the regular trapezoid, because it's the one you see most often. But an isosceles trapezoid is technically this, with the congruent legs. But regular trapezoids can be anything as long as the 2 sides are parallel. And so they can look kind of funky, but you have some that are always staying. 2 segments that connect it all together can be whatever you need to make it happen. Okay. A rectangle is technically a type of trapezoid. Yes. Same with the square. Right. Mm-hmm. Because I don't know. I don't know. So we've got these guys that we're going to work with. Trying to think of what other ones that we might need. We've talked a little bit. We might as well put, even though we've talked about it some. We'll deal with these as well. Just an isosceles triangle. That's another one we're going to work with in this section. See the relationship between the isosceles trapezoid and the isosceles triangle? You see how the isosceles trapezoid is kind of like you took an The isosceles trapezoid is like you took an isosceles triangle and just like pulled it apart, like stretched it out and created a trapezoid out of it. Pretend like this here just got out over there. So it's like now it's a trapezoid. Okay. Yes?
For the isosceles triangle, should you do the congruent angles, like the base angles?
Yeah, technically we've got those angles in there as well. Really it's the sides that we're more concerned with, but same thing, right? Angles would be congruent then? And you've got angles that are also congruent, so we could put that in there too, that's fine. Okay, so these 4 shapes though basically are the ones that we're going to focus on. And to do a coordinate proof is to take a shape, put it on a coordinate plane, and prove something about it. Okay? So we're not going to actually get the proving of things until tomorrow. Today we're just going to focus on how can we take these shapes and put them on a coordinate plane. And the trick is going to because putting these in a coordinate plane, I think everybody in here can do. If I gave you like how big they were, like a rectangle that was like 3 by 2 or something like that. But we're not focusing on that necessarily. What we're focusing on is if I have like a generic rectangle or a generic square. Okay, so I don't have some measurement to give you. With how could I describe where the coordinates are on the coordinate plane if I don't know how big it is? Okay, so we're going to do next. So we're going to take each one of these and we're going to try and put it on a coordinate plane with generic coordinates. This is going to be the first step. If you want to prove something about one of these shapes and you're going to do a coordinate, but you have to know how to. Okay, so first, let's say 10, you would like to include 0, 0. Just put your phone away. You would like to include 0, 0 as one of the corners of your shape. Okay? Now, depending on what kind you're looking at, you might not want to, but most of the time you do. Now, remember I said this is supposed to be like a generic square. Now, I know I used 9 boxes to draw it, so it's like a 3 by 3 as far as the boxes are concerned, but let's say that I really don't know how big it is. Okay? So I'm going to use a variable for its dimensions then. Okay? And so let's just use A. Okay? We can't use X because X is the x-axis. Okay? So we started using X as the dimensions in here, it would just get confusing. So we use other letters, so like A, B, C, D, that sort of thing. So this square, every side is the same length, right? So let's say every side on this square is a length of A. Okay. Of that point right there, then, if every side of the square was a length of A, it's not a number. Remember, we don't know that it's actually 3. So this length is A. So what are the coordinates? It's not AA. Somebody already guessed it. It's not 0A. A0, right? Right, because that went in the X direction, correct? So we went over this mystery number A, but we didn't go up yet, right? So X is A, but Y is still 0. We haven't gone up yet. Yes? What is it? This one right here? Yes. Okay. Sure. Because remember, so that would be over A, up A, right? So it's AA would be the upper corner there. It's in this case, yeah. For the square, yeah. Okay. No, not necessarily. The next one, we'll do the rectangle next. So, little variables in the appropriate way for what the shape is that we have. Okay. To really like prove something about. Yeah, there's a couple lengths that are different on there, right? So can I go like doing all the A's like I did on the last one then? I can't go A all the way around. We could do like A and B maybe. Again, I know it's 3 boxes one way and 4 boxes the other, but remember we're trying to kind of assume this is a generic rectangle. So we want to use variables with it instead. So again, we got this thing at 0, 0. What would be the coordinates over here then? B0 this time. What would be the coordinates up here? Careful, right here. Is it 0A or 0B?
0A.
It's 0A. So remember, A is up and down, right? B was the width of it. So just be careful, okay? So think about how you get there. From 0, 0, you would go up, and now we're at 0A. Over here, we went over, so it's B, 0. What's the corner this time? Yeah? BA. Yes, I know the jokes, just I get it, all right? Now, here's the difference with the other two. Anytime that you have a shape that has a certain amount of symmetry to it, like I could put a line down the middle of it and break it in half, we don't want a corner on the origin anymore. So the isosceles trapezoid, the isosceles triangle, all right, it's less helpful to have that thing on the origin. Okay, we can try, but I'll show you. I could show you. It gets really messy. But if we instead put the y-axis right down the middle of it, it makes it easier to work with. Okay. We're still putting these on the coordinate plane. Yep. So, well, it's going to be like this time. So, yeah, it's going to be on the x-axis if that's what you were asking. We're going to have half of the isosceles trapezoid on the left of the y-axis and half of it on the right. So it looks something kind of like this. Okay. Now the reason that I did that was because I know no matter how big this isosceles trapezoid is, if like this is exactly half of it and this is exactly half of it, right? Has to be that way with that isosceles trapezoid. Here to assign to some of the coordinates, okay, we got to come up with some different dimensions on this thing, okay? So we got to think about what do we need, okay? So let's start with this point right here. Use whatever letter you want, but what has to be the variable, the x or the y coordinate? The x would have to be variable. So we know what? 0, right?
0, right, yeah.
Okay. Oh, didn't mean to do that. Thank you. Okay, so the y is 0 there. The x, I can make it again whatever letter I want, so maybe let's go A. Okay. That's nice. Okay. Now, see the point that is the reflection of that point? Okay. Negative A, 0, right? Okay. So what we're saying then is that this is a distance of A and this is a distance of A, right? Because I had to go from 0, 0, I had to go over A to get to here, and from 0, 0, I had to go over A this way to get to this one. Okay, now these two up here are tricky. Okay, remember, A is the distance from here out to here. Am I going to have A anywhere in this one?
No.
Has nothing to do with that point, right? This could be wherever it wants to be, and this could still be A, and who cares? It would still be an isosceles trapezoid. So, the coordinates of this, I'm going to have to use 2 new letters. go BC on it? Okay. So I had to go over B. That distance right there from here over is B. And then what is C? It would be how it is, right? So that's kind of your C there. This is BC. Be the coordinates of this point over here. Negative BC. Okay? So I'd actually need 3 different measurements on this thing to figure it out, right? I'd have to know the length of this base, the length of this base, and the height of this thing to be able to get where all these little coordinates are. But you can see it like that then. Yeah. Okay. All right. And let's do our isosceles triangle, and that'll be the last one we try to fit together onto the coordinate plane like this. One is symmetric down the middle as well. Thing here. All right, so let's start with that bottom right corner again. So what could I do with that? Based on how we've been doing these, I think would make a good choice for naming that one. A0 again? Sure. Mean that this distance right here is A. Okay, what's the other one then? Negative A0. Okay, and then we've got this last one up here at the top. We could do 0, yeah, and call it B. Make that height up the middle of the isosceles triangle B. Okay, so this is what I mean by we're going to look at generic shapes. Okay, we're not going to actually have numbers attached to any of these. We're just going to keep using these letters, and we're going to try to prove certain things about it. Like we might prove, let's say, in the isosceles triangle, that these two segments are the same length. Okay? Or we might prove that this bottom part of the triangle here is perpendicular with this segment right up the middle. Something like that. Okay? Those sorts of things. But these proofs are a little bit easier because you don't have to sit there and do the 2 columns, do all the logic, all of that kind of business. Instead, if you can do a calculation with it and show that both, like if I wanted to show that these 2 segments were congruent, if I used like the distance formula, calculated it here, calculated it there, and show that they come out to the exact same thing. It won't be a number. There'll be something with letters in it, with the A's and the B's and all that kind of stuff. But if I can show that they're the same thing, haven't I then proven that they're the same length? Even with A's and B's in there, I can do that. Okay? That's called a coordinate proof. And for some people, it's a lot nicer. They like to do these a lot better. If I take some kind of shape, if I'm talking about triangles, whatever, and I want to put it on a coordinate plane and use that then instead to prove that something's the case, you can. Okay? Question?
You said the distance formula. Could you just use the Pythagorean theorem?
Yes, you could. Mm-hmm. So that's the sort of thing that we're going to be looking at in the future. There's a question over here. Did you have your hand up, Gabby, or not?
Yeah, but it was really off topic. I was wondering why your lines got so straight.
Oh, I don't know.
He's so used to
Oh.
drawing shapes that happen.
He's got ruler hand.
I have ruler hand. I'm afflicted. All right.
You got a thickness now?
So let's just do one of these. Okay, this will be. Well, maybe we'll have one of these, and that'll be it. Now, we'll be doing something a little bit more complex than this, like when we really get into it. But for today, let's just do what I said there with that last triangle there. So let's prove, using the distance formula, that the two sides of the isosceles triangle are congruent. So the first side, we've got negative a, 0, and 0b are the two coordinates. Okay? So, and yes, you could use Pythagorean theorem. However, I'm going with the distance formula here for this one. So I said to use it, so we're going to use it. So the distance formula for those 2 points, remember the distance formula? Big old square root. And you do y2 minus y1, so in this case it would be b minus 0 squared, and then plus 0 minus negative a. 0, yeah. Okay. Now it's got b and a in there, but we can still simplify that thing up a little bit. So it becomes the square root of b squared plus, what do we get with this? We got 0 minus negative a. So that'd be a squared, right? Yeah. Okay. Can I simplify it down anymore?
No.
Square root of b squared plus a squared, isn't that just b plus a?
Yes.
No, it's not. Careful. You can never distribute a square root. It doesn't work. So the square root of b squared plus a squared is not b plus a. It is just the square root of b squared plus a squared. Okay? So, second side, the 2 points for the second side would be a0 and 0b, right? These two? So let's do the same thing, okay? So with a0 and 0b, the distance... Please stop. I didn't say it was. Okay. Alright, so square root of b minus 0 squared plus 0 minus a squared. Then if I plug things in the distance formula where they're supposed to go for that one. So then I get the square root of b minus 0 squared, again, is just b squared, right? A minus, or 0 minus a is negative a squared, but negative a squared is just a squared, right? It's the same thing, because negative times a negative is a positive. Okay? And because I end up with the same thing for both of those two, I've proven that those two segments are the same length. Even though I don't know their actual dimensions of how far up and over they go out, I know they're the same because I got the same thing when I did the little formula for them. Okay? So, all right. We're going to stop there for today. We'll dig in a little more with the proving of things tomorrow. Everybody hold tight, though, for the last 7 minutes because I want to pass back stuff to you, including your last quiz. So I don't want to lose you. So stay put.